Hello, and welcome to Module 2 of Foundations of Machine Learning. So first, with assumptions, in this module, I'm going to assume that we have a small synthetic student trials account dataset. It's two-dimensional features that we'll have, like just to make examples more concrete. What we want in the decision context, like the scenario we're going to have, is we're going to decide who to flag and who to nudge in an online learning platform, like whether we should send an email to subscribe or to follow up. We'll say subscribe for now. The math depth will be light, so we're going to have definitions, simple formulas, some toy examples, but we're not going to be doing any proofs or anything like that. And prerequisites before we start, you're going to be comfortable with Python, Jupyter, NumPy, Pandas, and some basics of supervised learning already. So by the end of this module, you'll be able to define supervised, unsupervised, self-supervised, and semi-supervised learning in terms of the data that they assume you have. You'll be able to write down a very basic objective for a supervised risk minimization task. You'll be able to classify real-world problems into appropriate paradigms and justify the choice. You'll be able to diagnose when a paradigm's assumptions are violated and what failure modes to expect. And you'll be able to some extent, connect modern systems like GPT-style large language models back to these paradigms. So let's consider kind of the basics. X and Y. We're going to use this notation as much as possible. It wouldn't always be colored, but just for simplicity now it is. Capital X normally refers to a matrix. So capital letters are matrices. Lowercase letters are vectors. I should move that. There we go. So yeah, the input data will be a matrix of shape ND. That's N rows and D columns. So we'll have a certain number of examples, like students, patients, or transactions. In this case, it's students. We'll have a certain number of features per example. So in this case, D is going to be equal to 2. The Y, in this case, is what we're trying to estimate or predict. This is the target. We care about this. This shape is an n-dimensional vector. So the way we normally describe that is n comma nothing. That just means it's a one-dimensional vector, like you can see here. So every row we can conceive of as a single data point. Not that it matters, but here's the code that I used to construct this table. So we have just two variables. We have the time on the platform in total number of hours and the average quiz score. So this particular student spent 1.2 hours on a platform and got a quiz score of 55. And we also know that they ended up not subscribing to this course. Then we have other data points where people spend a bit more time, they get higher quizzes, and then they end up staying in the course. So again, not too important, but because all of this is going to be stored in data frames in Pandas, we can access them by referring to their column names like this. We can obtain the values for X and Y. So I care about the will subscribe column as a target. I get its values are stored in vector Y. And then you can use the shape function on these to get the overall shape, and it is as we expect. There's 3 rows with 2 columns for our training or our data X, our input data X, and a 3-dimensional vector is what we're trying to predict. So what do the data points actually look like? So here's the code that I use to produce the image you're going to see in a moment. So this is essentially the same world. So the exact same data was acquired in both the image on the left and the image on the right. On the left, we have the X and Y coordinates of all these dots. That's sort of the input variables. I should say this is X1 maybe is the horizontal and X2 is the vertical. Not to confuse it with Y, which in the case on the left is the label. And the label Y is either purple or yellow, or 0 and 1 respectively. Okay, so we have the geometric location of these dots in space in terms of horizon and the vertical, and then we have labels in supervised case and no labels in the unsupervised case. We have no differentiation in the unsupervised case. So the learner, we can still learn from unsupervised data even if we don't have a label. we just have this kind of cloud, or two clumps of data points X, and we have to discover if there's a structure there without using any labels. So the unifying idea in both of these cases will be that we'll just learn from the data. So in both cases, we're going to have input features. Data X, whoop, there goes my camera. Let me just zoom out for a second here. There we go. Let's keep it that way. We have input features X, like small x is a data point, which is an element of big X, which is all of our input data, which is images, tabular records, like in a table like we saw a moment ago, maybe just raw text. Then we'll have targets or labels. These can be classes, like purple or yellow. These can also be real numbers. We can try to predict, someone's actual mark on a quiz as opposed to whether or not they're just going to subscribe or not. We can also predict the next token if we're dealing with text, as we'll see later in this course. Just predicting the next token might be our target. And in all of these cases, in supervised learning, we'll have access to Y. And we can assume that the data we observe, the X's and the Y's, come from some probability distribution. So this is more or less, this tilde here means that it's sampled according to some probability. So there's some kind of hidden probability in the world that we don't necessarily know beforehand, but we can discover it, and we can use that discovery to help us make good decisions. So in this course, basically, like we mentioned earlier in the previous module, we want to learn some function, call it f sub theta, where theta is our parameters, that maps X onto Y, and especially will perform well on new samples from the same or similar probability distribution. So here's kind of what that looks like. Here's the code I used to generate this pretty graph. So if you look from it from the top down, this is kind of like the two clusters we saw earlier. We have yellow and purple here. So we have time on the platform in hours. This comes from our data set, and average quiz score is the other input variable. So these is kind of the base here. These two dimensions are our inputs. And what we want to predict is the probability that they will subscribe. Okay, and all of these dots here refer to a data point. So we have a data point at like 6.5 and 68.9 approximately, for example. So this kind of step-looking like thing here is really a form of regression. We'll talk about it later, but you can see it kind of classifies like all of these points down here. The probability of all of them subscribing is very low, and we kind of know that they don't subscribe. And up here are the data points for people who do subscribe. And this curve that we've drawn is really the probability curve. So if we observe a new data point in the future we've never seen before, down here at location 6.77 40.42, the probability that they're going to subscribe is very low, right? They have too low of a score on the quiz, even if they spend a lot of time on the platform, so that we don't think they're going to subscribe. Somewhere in the middle here is where it gets trickier, right? So the probability of somebody subscribing here is about 75%. We can get it down to 50%. You can play around with this yourself, but you can see how we have our data points. We have learned, a manifold or surface, which represents our probability function. And then we can also look at arbitrary other points, which are not found in our training data, like down here. And we can still estimate the probability of subscribing given this data I've never seen before. So I think I've described all of this. The key thing here, once again, just to make it, just to emphasize this, is that this probability function is fine for learning on our training data. Sometimes that's all you really want to do, but often what we want is to be able to make predictions about other things we've never seen before. So why do we care? Well, it's kind of like a game to some extent. You can think of it as a game. We want to use data that we have, so the training data, to build that model or that function, f sub theta, and make it perform well on data we've never seen before, so future samples, right? Like if you're trying to build a new app that uses AI, to some extent, it's great that it works well on your phone in your setting, but you want to make sure that it works in the field on other phones and other locations. So here's the code for this little graph. This kind of highlights this instance, which I kind of mentioned already. We have, again, a scatter plot of training data. I've seen data, both the blue and the orange. And all of these X's, like if we were sampling from that probability distribution I mentioned, the probability distribution that provided these blue and orange circles, if I kept on sampling from that distribution of probability, you can sample these x's that are kind of scattered all over the place. And generally these x's that are close to these orange dots are probably going to be classified in the orange way, and those that are clustered around the blue dots are going to be clustered in the same way as these blue dots. Every metric we are going to compute on a test set is basically trying to estimate how will this model behave in the future from this process. Okay? And again, if we're only winning on the points we already have, good for you, but that's not really learning, that's memorization, which is a bit different. So this is similar but not exactly the same as thinking of machine learning as a small time travel experiment. So in some sense, we already have some data, and we've acquired it over time. So we've acquired the step counter or something from a smartwatch over the course of several days, and we want to make predictions about how many steps the user is going to have on day 11, 12, 13, and so on. So we have a data set. We call it x sub I, y sub I. These are our inputs and outputs. X sub I can be a vector of numbers, right? We have several measurements. We have n data points, so we have everywhere from I equals 1 for the first data point to n, whatever that might be, from the past, and we want to estimate we're going to have a new x star in the future, we're going to have new measurements in the future, and we want to make decisions about y star without necessarily knowing that. So, one way of thinking about it is training a model f theta to help with tomorrow's decisions. Not just to explain what happened previously. That's not always the case. I want to emphasize that. Sometimes we want to use machine learning really to uncover what happened in the past and help explain it and help discover the signal and the noise. But here's one helpful way to sometimes think of machine learning. Definitions. So this is going to be important for you to come back to. Supervised learning first. In supervised learning, our data consists of inputs, x sub I, and labels or outputs, y sub I. For n data points, we'll call this data set script D sub sup for supervised. So our objective is to choose the parameters theta to minimize the expected loss. So again, the loss is going to be a difference or like an error that we want to minimize. So here the prediction of the model f sub theta given an input x is one quantity. We want to compare that against the actual observations y, which is like the true labels. This loss function, like we saw in module 1, will give us some error signal. For now, it doesn't matter. It could be an error signal of 1 if it's wrong, or an error signal of 0 if it's correct. And over any data set xy that's obtained from the probability distribution that describes our data, we have the expectation of the overall risk, or the overall average loss over all of the possible samples. This will be the risk of this particular parameterization theta. Okay, so we can tweak theta to minimize this expected risk over this distribution. This is very theoretical. Normally we don't have the true probability distribution, and we certainly don't have an infinite number of data points. So instead we minimize the empirical risk. Empirical risk is just more of a practical way of describing risk. In this case, we have, again, our n training samples we talked about a moment ago. We'll have a loss, like a difference or an error signal that says, well, you get an error for data point 1, the prediction for x sub I is different than what y sub I is. And we'll take the average, so we'll divide by n, and that's it. Unsupervised learning, we don't have the labels again, right? So we call this script D sub unsup for unsupervised. We still have n, well, n can vary, right? N can be anything, but we have n data points. All of them are just inputs, x sub I. So we have like the location of data points, but no labels. But our objective now is to discover the structure in X. So we just want to figure out how X is shaped. We can do this by clustering. So we can essentially partition the indices, so all of our data points, 1 through n, into subgroups. Subgroup 1, subgroup 2, all the way to subgroup k for some specified k. So that when we have points in the same subgroup or cluster, we can say they're more similar to each other within that cluster than to others. So all of the data points we've partitioned into subgroup I will be similar to each other within I and very different from the points in some other subgroup S sub j. We'll talk about this in greater detail in future classes, but essentially, like, we can talk about density models. Density models are probability distributions. They have parameterizations also, so we can still set the parameters, but they describe sort of a probability distribution over X. This tells us like how likely are the different regions in the feature space. So we'll get back to that later, but we can cluster according to probability distributions. So you can think of supervised learning as predicting a label, and unsupervised as either explaining or compressing data, or maybe even just finding patterns within the data. So just briefly, again, we'll come back to these later also. This is, so I put this little kind of microscope here to indicate that this is like digging into some detail here, but the detail is important. Self-supervised learning, again, we only have data, like input data. We still don't have labels technically. So it's still kind of like an unsupervised case, but we can create pseudo-labels from the data itself. The task is set up in such a way that we can use the data and manipulate it in order to get pretend labels that is going to help us train a model that we can then use for some other task. So next token prediction in text is basically something like self-supervised learning. So technically we have, say, a lot of text. In supervised learning, we might have a label. This text comes from a patient with a disease. This text comes from a patient without a disease. So we have a label, so we do supervised learning. Now we just have text, so we don't have any labels to supervise us. But when we use a model to predict what the next word should be, gradually we should learn a difference between those two groups, if it exists. So we just like the label that we're trying to predict is given the previous words in the text, just predict the next one. And if you do that very, very well, you must have learned something about the structure of the language and the source that produced it. At least that's the theory. We'll come back to that later. Masked word prediction. So I cite BERT here. Maybe I should just cite the actual paper also, but there's a paper that doesn't just try to predict the next word in a sequence, but kind of predicts any word within a span of text. That's BERT, one of the first transformer models of language. With images, you can take images and then you can just apply rotations to some and not others. So imagine you take an image, you rotate some of them 90 degrees, other of them you don't. That is your label. Did I rotate this image, yes or no? A model looks at these images. It'll be provided that label, rotated or not, as if it's a supervised task. But we haven't gotten that label from anything outside. We've provided that label ourselves by performing rotations on images or not. Okay, so again, we're not given any external source of labels, but we're kind of just tweaking things so that we can do something like supervised learning, but on a label set which is totally synthetic. Finally, semi-supervised learning is a combination of supervised and unsupervised learning. We have some label set with n sub l samples in which we have labels y, and then we have larger, usually unlabeled data set d sub u, in which we have n sub u labels. So our objective is to use both d sub l and d sub u to learn a good predictor for y. One thing we can do is we can do some clustering of all of our data, the union of d sub l and d sub u. Data points that fall in similar clusters probably have similar labels. At least that's an assumption which we can make explicit. We can assume that there is sort of a probability region within nearby points that is smooth and not too jagged, that allows us to make these kinds of assumptions. But we can basically do unsupervised learning and then do a little bit of supervised learning on top of that. We'll give you examples of these later. I'm just sort of providing initial definitions. So here's some clustering visually. So in this case, I produce some data manually. So I have like these three normal distributions in 2 dimensions in which they have their means and their variances. We're actually doing k-means here, so we're jumping ahead a little bit. So for now, it's just as an example, but the sklearn cluster library has kind of a class called k-means, which allows us to learn the clusters. So first we say, well, I'm going to be looking for 3 clusters. We set a random state. This is all good to do stuff to make sure it's reproducible. We set a random state. We set an initial n init to 10. So this is, we just set it up, and then we actually, given the data we've produced synthetically, we can use fit predict to identify the clusters. And then once we have those clusters, I just kind of color it, right? So these are 3 clusters that I specified, and then I generated the points synthetically, and then I used k-means to identify those clusters. So it's a little bit circular, a little bit easy, because I knew that those clusters were there. But the k-means found these clusters automatically, and then it colored it, and we colored in these dots. So like these data points weren't initially given a label yellow and a label purple and a label turquoise. This is what k-means got for us. So yeah, each of these colors represent a cluster. These are groups of points that the algorithm judged to be similar according to some measure. Again, we didn't provide any labels. Any clustering is only based on like the geometry of X, so it's horizontal and vertical position of the dots. And k-means is super popular. We'll define it and analyze it carefully in a later module. It's not necessarily the best in all situations, but it's very popular. So let's do a quick anti-example, so ways that things can go wrong. Imagine we have 100,000 customer records with features. So we have input features. And for 500 of them, we have future revenue. So we have some label Y, which are real valued targets we want to predict. So we know that when we have unlabeled data and we have labeled data and we combine them together, this is potentially a semi-supervised regression because it's half supervised, it's partially supervised. And we're doing regression as opposed to classification because we're not trying to predict classes, we're trying to predict real valued targets. But if all you're doing is clustering those 100,000 customer records and that's it, and then getting labels like we saw on the previous slide, that isn't exactly labeling or learning from labeled data. You shouldn't call it semi-supervised learning just because you have data sets of this type. So we never use the labels in our objective, therefore our training is purely unsupervised, it's not semi-supervised. And if we evaluate clusters using revenue, like if we after the fact go in and kind of compare our clusters against the revenue generated by these 500 people, this is after the fact. This is what we call post hoc, afterwards. So yeah, we're not calling it semi-supervised regression might make you look smart initially, but when people find out what you actually did, that will make you look, let's say, less than smart. So what makes something supervised versus semi-supervised is really how labels enter the objective. It doesn't really matter that labels exist somewhere in your database. It really matters like how and when the labels are used. So again, we have this simple task. We have a binary classification task now. So now we're doing classification. We have outputs 0 and y, and we have just one variable now. So x is just one number here in this column. We have a target y, which we're trying to predict. This is a binary outcome. And then imagine we have a model that's already trained. F sub theta of x gives these predictions over here. Sometimes, as you can see, the prediction is correct. So we predict 0, and the correct answer is 0. Sometimes we predict 1, and the correct answer is 1. And sometimes we get it wrong. How does this translate to our empirical risk? Well, remember our empirical risk, or R, say hat theta, is just the average loss over all of our data points. We have 4 data points, so n is 4. And what this means is more or less that our loss function is just 1 if they're not equal. So we perform this inequality, and if our prediction and the actual label y are not equal, otherwise if it's true, then we count a 1, otherwise it's a 0. So going down this list, you can do this yourself. Them being unequal is false, therefore we add 0. And then for the next data point, them being unequal is true, therefore we add 1, and so on. And then because we have 4 data points, we divide by 4, giving us an overall empirical risk of 25%. You can think of this somewhat as a classification loss or empirical risk in which we get 25% error. So not accuracy, but error. So the key idea here is that supervised learning will make as few mistakes as possible on future data into something specific, which is minimizing the empirical risk on a sample. There are other controls we'll add later to this. This is like the simplest way of doing it. We'll come to this later. Loss is a measure of error for a single data point on the average error across the training data. So in this case, we're doing with this function, which I'm calling 1 here. But before we saw mean squared error in module 1, the loss function will change depending on what your task is. Again, the risk is the expected value of that loss over the entire unknown data distribution. It's somewhat probabilistic. It is calculated specifically for the training data, but it's a rough estimate for how much error one might expect in general if we kept on sampling more data. So let's see a somewhat more fulsome example. We're going back to our synthetic student trial accounts dataset, in which we have input features, which is time on platform, which is a continuous variable measured in hours per week. And we also have as input average quiz score. We're doing supervised learning, so we also have a label as to whether they will subscribe or not. Now, we don't normally only care about being as accurate as possible for its own sake, but we want to use these models to help us make better decisions in the real world. And what kind of decisions can we make? Well, maybe we want to send a little nudge email only to those individuals who are possibly going to subscribe. Okay, so if someone seems like we think they're going to subscribe, we can send a little email to them to get them to join. This is a bit of domain expertise, so I can imagine that people who are going to join anyway might not need that nudge, but we'll leave it as the story for this example. There are kinds of different errors we can make. So there's a false negative. A false negative means that, well, we predicted that the individual was not going to subscribe, but they were going to subscribe. They actually were a potential positive case. And then therefore, in this scenario, we would not have emailed them to nudge them into subscribing. And then therefore, this is like a missed opportunity to increase engagement, right? We predicted that they wouldn't care, so we didn't bother reaching out. There's a cost associated with that. It's cost other than loss functions. It's like a real world cost. There's false positives. So a false positive is like, well, we thought someone was going to subscribe, but really they didn't care at all. So they get an email. That's going to be annoying to them because they're like, why am I getting emails from this platform I don't care about? That also incorporates a slight real world cost, but it's different than the other cost, which is a concept which will keep coming up over the course. So we can use scikit-learn to do some supervised learning. So again, we're getting ahead of ourselves a little bit here, but just to demonstrate how this works, you can go ahead into the slides and copy this and run this yourself to make sure everything works. But what I'm doing here is I'm basically producing random data, getting X's and Y's, like inputs and outputs for these, representing them as in a data frame in pandas, splitting them according to the train test split in scikit-learn. I want to have about 25% of my data reserved for testing. The random state is 3151, and so on. I'm going to do a logistic regression like we saw earlier. I'm going to fit it, and then I'm going to do my predictions. And we'll come back to this later again also, but we're going to produce a confusion matrix. And the confusion matrix is shown here. So this basically compares the true label from the actual data versus what the model is predicting. So there's 0 instances where the model predicted the person was not going to subscribe, but they actually did. And there's 40 instances where the model predicted somebody was not going to subscribe and they didn't. Similarly, there's 40 instances where the model predicted that they were going to subscribe and they truly did. So everything looks good here, right? So generally with confusion matrices, we want our predictions and our true labels to match up, and here they do perfectly. So here, like all of our data points are on this diagonal, and nothing occurs in any of the possible error cases. So again, warning: normally things won't look this nice. There'll be a lot of errors popping up all over the place. This is because the synthetic data set is nice. It was set up in order to get the results this way. Logistic regression, can get very high accuracy in practice as well, even on noisy data. But in real life, the labels can be noisy. So maybe the true labels we're provided with have some error in them somehow, or they're not really true labels, they're just approximations for the truth. The train test split can also change things depending on how we did that. Again, we did this here somewhat randomly, as you can see. And we're only dealing with accuracy, which is fine in this case, but what if we had a ton of false positives or a ton of false negatives? How would that show up? That's going to matter to us. So what is the model really learning? Well, we can visualize the learning process. So we can take the same example. We can visualize it more or less top down. This is very similar to the 3-dimensional plot we saw earlier. The color field here is basically a representation of the model f sub theta, and more specifically the model's estimate of what is the probability of the outcome being y given the input x. So the input x is one of these dots, and the color that you see is more or less like the probability, which is yellow if it's high and purple if it's low. And the contour here, this kind of turquoise area, is where all the interesting stuff happens, in my opinion. The second example is an unsupervised clustering on the same data, so the exact same data. Now, like even though we had labels for the logistic regression, imagine we never saw them. So when we run k-means, we get, using this code, we get this graph. Usually the clusters align nicely with the labels we saw previously. So the clustering here and the labels we were provided with usually are pretty good. But as you can see, there are some instances where the automatic clustering has labeled these points over here on the left as, as being more similar to the purple class, the positive class. But in reality, they're quite close to the yellow class or the negative class. So the colors are flipped here, but that's not important. So this is a little bit important. The algorithm has no idea really what subscribe means. It only sees the geometry. But it seems to do mostly a good job. These big X's here represent more or less the centroids or the centers of these clusters. We can quickly get another, I think this code actually generates another confusion matrix, which compares kind of a cluster label against the true label. And even though the labels are reversed here, more or less like things, this is the inverse, so things actually do match up pretty well. And even though this looks like they're in disagreement most of the time, it's only because of how we've colored things. So generally, this clustering has most of the time has identified the two groups very well, with some exceptions, like you can more or less see here, right there. But that's as maybe. Our evaluation must always match the decision, right? So for our subscription sort of scenario, our stakeholders, people who are distributing this platform, care about how many future subscribers we catch. So that's what we call recall. We'll return to this later. We want to grab as many as possible. We want to maximize recall. We also care about how many people we annoy unnecessarily. So we want to send emails, only to people who are more likely to respond. We don't want to annoy people unnecessarily. That's not going to be a good look for us. So we want to maximize the precision also. Accuracy is not exactly recall or precision. They're closely related, but accuracy treats all mistakes the same. It doesn't care if it's false positive or false negative. So you should always ask, if a model makes a type of mistake, who gets hurt and how badly? And what is that? What is the nature of that pain? There are going to be various kinds of evaluation choices we can take. We're going to see in this class precision and recall, so-called ROC curves, calibration curves, like are the probabilities we're learning actually honest? For unsupervised clustering, if there are no labels, there'll be measures related to cohesion within a cluster or separation between clusters, how stable the clusters are if we try this clustering algorithm again and again, and so on. Again, I like to conclude by thinking about ethics and fairness and robustness. So even in our little toy example, if our labels, will they subscribe or not, if it encodes historical bias or supervised, like semi-supervised models, they'll inherit that bias. Okay, so maybe certain kinds of demographics are more likely to respond than others historically. Maybe that's no longer the case now, but if we learn from historical data, that could disadvantage members of those subgroups. Self-supervised objectives on logs or text can memorize sensitive information if you're not carefully anonymized or regularized. So we're going to need to apply some privacy protection to our models. Semi-supervised learning can also assume that unlabeled data comes from the same distribution as the labeled data. And this is also true of supervised learning, actually. So when we train a model with labels, we can assume that the process generating these labels is going to be the same in the future as it is today, but that's not always going to be the case, right? So especially new diseases come on the scene, there are seasonal changes that occur yearly, so if you don't have lots and lots of data over many years, you'd miss that. So you want your models to be robust against shifts in the data, and that's an important concept we'll keep on coming back to. So evidence we always have to demand. Will the performance vary by subgroup? Do we have tests of robustness under shifts in the distribution, the probability distribution that's generating the data? That means that we can do a good job in making predictions, whether or not we're predicting things currently or in the future, or even maybe in the distant or the recent past. Does this model work on the Studley campus? Does it work on the Sexton campus? Does it work on the SMU campus? Using students in those different environments, we want to be robust against all of those different scenarios. And as always, how do we document things and how do we talk about our approach? In our earlier example with that X, the what not to do, the anti-example, we saw somebody describing their training process in a manner that was incorrect. We never want to do that. We always have to try to appeal to the truth. So how is GPT self-supervised? So modern large language models are mostly trained using self-supervision. That's where we have some unlabeled data, and then we make some modifications, and then we try to predict those modifications. It's not universally true, but it's fairly common. So data can be like a massive corpora. Corpora is just a data set of text, and often there's no human labels. I mean, in reality, there's certain situations where you do have human labels for certain things, so it becomes a semi-supervised, semi- and self-supervised training. Their task is usually, as you probably know, it's well known at this point, the task is just to predict the next token given some previous tokens. And just doing that by itself can expose all kinds of important knowledge about the source of the source that produced the text or the probability distribution that produced the text. Our objective on that task is to minimize what we call cross-entropy. Again, not to sound like a broken record, so to speak, but we'll come back to that later too. This is a supervised loss on this kind of synthetic task. So even in the most modern models that are being produced today, we still have to deal with data, and we need to care about whether there's labels or not. We need to know what the task is, and we need to know what the objectives are. So everything we learn today applies to the simplest logistic regression models and linear regression models, and it applies to GPT-5 and whatever comes out next. So this paradigm is self-supervised, but under the hood, there's lots of supervised learning on an automatically generated target. That's basically what self-supervision is. And we'll come back to this later. So just keep this in mind. If your pretext task is weird, what representations will my model learn, and which downstream tasks will that hurt or help? So this is something just to think about. Try to figure out what that means, jot it down, come to class with your questions, and as is often the case, go to the slides online, pause to think, answer these questions. These questions are not multiple choice in this case, so I expect you to just write down your answers. Bring these to class, and we will talk about them. Thank you so much.